Welcome back, Applied Calculators. In this screencast, we take a look at logarithmic functions. And we can't talk about logarithmic functions without going all the way back to this sort of textbook definition where we see a log and there's this little number down here and there's this number over here and there's this thing on the other side of the equal sign. And your textbook says that this thing is the same as this thing. Now, I have had a hard time understanding it this way. So if it helps you to understand things, I have traditionally written it this way. Every log is written with respect to a base. This little number here is called the base. And every logarithm is of some number. You don't just write the word log, it's always log of something. That something is a number. And a logarithm is an exponent. This number on the other side of the equal sign is an exponent. This y becomes an exponent. So a log is taken with respect to a base. There's always a base. A log is taken of a number. There's always some number here. And this is an exponent. This translates into base to the exponent is the number. This is unofficially called the Ben rule of logarithms. It is unofficial. There's no mathematician named Ben that came up with it. But it is a good way to remember what the relationship is between a logarithmic statement and an exponential statement. So that when we go trying to find the log of 81 base 3, well, what does that mean? Well, clearly it's some number that we don't know. That's the base, that's the number, that's the exponent. Base to the exponent is the number, and now we know that that question mark has to be 4 because 3 to the 4th is 81. So now we know that the log of 81 base 3 is 4. Similarly, we could ask for the log base 5 of 1 over 125. And we could ask ourselves, what is that? Well, that's smiley face. I don't know what that is. It's smiley face. We've got a base. We've got a number. We've got an exponent. 5 to the exponent is 1 over 125. Well, this 125, that's 5 cubed. But it's a 5 cubed in the denominator, which means that this is 5 to the negative 3, which means that smiley face is negative 3. The log of 1 over 125 base 5 is negative 3. And it's this sort of relationship that allows us to deal with all of the laws of logarithms. Oh, are these ever everywhere? The laws of logarithms. When you have the log of a product, that log is the same as add the logs together. Why? Because when you multiply powers of the same base, you add their exponents. When you multiply powers of the same base, you add their exponents. This almost makes sense. Similarly, when you have the log of a quotient, the log of a quotient is the difference of those logs. Why? Because when we divide powers of the same base, we subtract their exponents. Logarithms are exponents, so the rules that apply to exponents apply to logarithms. Couple others. When you have a log to a power, you take some number and raise it to a power. Well, that's the same as the logarithm multiplied by p. Why? Because this is m times m times m times m times m until you have p copies. And so we add the log to itself, to itself, to itself, until there are p copies. I will also note that the log of 1 is always 0, no matter what the base is. And the log of the base in the base is always 1. And it helps here to rewrite this as b to the 0 is 1, and it helps to rewrite this as b to the 1 is b to convince yourself, yes, this should be true, yes, this should be true. Those are so important. And in fact, this is what allows us to do the examples 4 and 5 that pop up in the reading. You ought to go back and take a look at examples 4 and 5 to make sure you can do them before we gather in class. One other thing we should talk about, and that's the graph of the log function. Let's take the log of x base 2. Well, the log of x base 2 is closely related to y equals 2 to the x. Y equals 2 to the x looks like this. Y equals log of x base 2 looks like this. Because of the relationship between the exponents and the logs. The point 0, 1 is on the exponential graph. The point 1, 0 is on the logarithmic graph. The point 2, 4 is on the exponential graph. The point 4, 2 is on the logarithmic graph. And these graphs are mirror images over y equals x. They are mirror images over y equals x because the way we got them was to treat them as inverses of each other. When we swap out x's and y's for each other, as we do when we convert from logs to exponents and back and forth, we reflect over y equals x. So if that's the case, then there's only one other thing to talk about. And that's that there's this function that we had talked about in our last lesson, y equals e to the x. So it has to have a logarithmic inverse that's a reflection over the y equals x line. And so this is the log of x base e. But nobody calls it that. Nobody calls it the log of x base e. Instead, we call it the natural log. It's the natural log. This is the natural log function. ln is French for logarithme naturel. It's French. The French got to it first. Sorry, we can't do anything about that, and they put their adjectives behind their nouns, and that's fine. So you want to be aware that on this function, this is the point 1, 0. This is the point E1, 2.718281828459045, 1. And it looks like every other log function in the world. It's got this increasing but concave down shape, and we'll prove that it's increasing and we'll prove that it's concave down once we know how to take derivatives of the log function. But that's another day. That's not this day. You have some things to go back and read. I will look forward to seeing you in class. Take good care until then.